Hi everybody, this video is going to be concerned about higher order derivatives. Essentially the idea is that we know how to find the first derivative, f prime, but because f prime is also a function, what that means is we might be able to actually derive it. And so that's what this word differentiability means and what it's referring to. What it's talking about is essentially the ability to derive. In other words, can we take the derivative again? And so if f prime has a derivative, in other words, if we're able to derive it, we notate it with a double prime. So you'll see kind of the double apostrophe. And so we say that that derivative exists at a point x in the domain of f prime. So essentially, if if x can be plugged into f prime and the derivative exists there, we say that f prime is differentiable. It means f double prime exists. Well, we say that f double prime is then called the second derivative. So we've got the first derivative, we now have the second derivative, and this kind of opens the door then that if I can take the derivative of the function to get f prime, I can derive it to get f double prime, then is it possible to continue deriving and get down into higher orders, so third, fourth, and even more than that if they exist. And so because we're doing higher orders, I just want to show you those notations. So I have those kind of listed out right here. Essentially, f prime you know of, f double prime we just talked about, triple prime is done with 3 dashes, and then this would continue all the way up. Sorry about that, until we get to f of n here. Essentially, the idea is after f triple prime, we stop using the dashes and we'll just use the number 4, then 5, then 6, then 7, etc., all the way to the nth derivative, which is what this stands for here, is the nth prime. And another notation that we didn't really look at, but I want to make you aware of, is this one with a capital D. The D just stands for derivative. The power on D tells you which derivative we're trying to find. And so these are kind of two main definitions that we could see and what you may see in the book problems and the practice problems I give you. Now, if f is written as y is equal to f of x, which a lot of the times we see, then what you can write in terms of for the derivative, again, things that we've seen before, y prime, dy over dx, and then dy. Well, if we continue taking the derivatives of that, you'll see that become y double prime, y triple prime. You could say y to the fourth, continue on to the nth derivative, dy over dx, d squared y over dx squared, d3y dx to the third, etc. And then using the letter d again. And so pretty much this lesson, it's pretty straightforward, pretty quick. The idea is just going to look at some examples and take higher order derivatives. You'll get some practice with chain rule and things like that. But after that, it should be pretty quick today. All right, so the first example I have for you is example 1. Find the derivatives of all orders of the polynomial function. F of x is equal to x to the fifth minus 3x to the fourth plus 4x to the third minus 2x squared plus x minus 8. All right, so go through and see if you can do this. Find the derivatives of all orders. So in other words, go through and find f prime, find f double prime, find f triple prime, etc. All right, so f prime, I'm just going to go through and take the derivative of each piece. So this would be 5x to the fourth minus 12x to the third plus 12x squared minus 4x plus 1. Again, the derivative of 8, negative 8 is 0, etc. Derivative. And when it comes time to find f double prime, I'm just going to derive f prime. So I'm going to look at this, what I just found, and I'm going to go through and derive it according to my rules. So the derivative of 5x to the fourth is 20x to the third minus 36x squared plus 24x minus 4. I'm going to take the derivative of it. This will be f triple prime, so the third derivative. This will be 60x squared minus 72x plus 24. Notice I can still take the derivative, so now I'm going to find f to the fourth, so the fourth derivative. This derivative will be 120x minus 72. I'll derive again. This will be the fifth order derivative. I'll get 120. And I'll notice if I go through and I take the sixth order derivative, I get 0. And once I get 0, notice it doesn't matter how many derivatives I go from this point on. The derivative of 0 is always 0, 0, 0, 0, 0. In other words, we found the highest order, which is the fifth right here. And we've reached the end. And so this is kind of the main idea. It's just once we find the derivative, we take the derivative again. Pretty straightforward. And so hopefully this makes sense. Okay, so that's the first example. I've got a second example. Now this one is going to ask just for the third derivative. But in order to find the third derivative, I need to find the first, and then I need to find the second. So we're specifically going to find the third order for the derivative here. And then it's going to ask us essentially what is its domain. All right, so go through and try that. All right, so I'm going to go ahead and start doing my work for this one. So I've got y is equal to x to the 2/3. I'm going to find the first derivative, incorporate the power rule. So 2 to the third will come down. And then I'm going to subtract 1. I told you the shortcut for this is to do top minus bottom. So 2 minus 3 is -1, and the denominator stays the same. So 2/3 minus 1 is -1/3. And so here's the first derivative. Well, again, I need the third, so I'm going to go through and derive that. -1/3 will come down, so this will make -2/9 x, and then again, I'm going to subtract 1. -1 minus 3 is -4. Denominator stays the same. And so this is the second derivative. Again, I want the third, so this is going to be my last and final time. -4/3 comes down. This will give me +8 over 27. X, -4 minus 3, -7, all over 3. And so here's my third derivative. Now it's asking me what is the domain. So in other words, what am I allowed to plug in for x? And to figure this out, what I'm going to focus on is this negative exponent and get this rewritten, because what that negative exponent does, remember, is it flips x and puts it in the denominator. And so if I was to rewrite this, I would rewrite it as 8 over 27x to the 7 over 3. And because x is in the denominator, what that means is x cannot be 0, but it can be anything else. And so in this kind of problem, that is my domain. So the domain is all real numbers. Except x can't be 0. All right, I've got the third example for you. This one now we're finding just the second derivative. So we're kind of like decreasing the amount, and it's really just because of the complexity of the derivatives. You'll see how this one will get kind of nasty fairly quickly, and it's mostly because of what the problem looks like originally. So for this third example, go through and find the second derivative of the function y is equal to, in parentheses, 2x squared plus 3 raised to the 3/2. All right, so I'm going to go through and solve this one so you can see kind of work behind it. I need to find the first derivative. To find the first derivative, notice that again, because I have parentheses, this is going to be a chain rule, where this is my g, the outside is my f. And so I'm going to do the derivative of the outside first, essentially acting like the inside's not there. And so this would be a power rule. So the 3 over 2 will come down. The inside stays the same. And I'll subtract 1. So 3 over 2 minus 1 is 1/2. And then I will chain this by now deriving the inside. I want to know what g prime is. So the derivative of 2x squared plus 3 is just 4x. And so what I'm going to do at this point is I'm going to go ahead and simplify this before I take the second derivative. This 4x, because it's being multiplied, I'm going to multiply it with this 3 over 2 up front. And notice that essentially what I'll have is 3 over 2 times 4x. This is over 1. And so the 2 and the 4 here can simplify down. This will simplify to just 6x. And what's in parentheses will stay. I can't bring the 6x in because of this 1/2 power. And so this is my final for the first derivative here. And I need this because I need to find the second derivative. So I want to simplify this as much as possible just to make our lives a lot easier when it comes to doing the second derivative. And that's probably my biggest tip as you're going through and doing practice on your own, or even just working through this problem. All right, so we need to find the second derivative. And again, looking at this big picture, notice that essentially we have one function times another function. And overall then, I have to do product rule first. And so I guess what I'll do is I'm going to call 6x is going to be my f, and this 2x squared plus 3 will be my g. And then remember, product rule is f prime times g plus g prime times f. All right, so I'm going to find f prime first. So the derivative of 6x is 6, and I'm going to leave g alone. And I'm going to add with this g prime. Now, this derivative of my second function here, this 2x squared plus 3 to the 1/2, it's chain rule again. Notice the parentheses in the inside and outside. So I'm going to do the derivative very, very similar, except this time what I'm bringing down is the 1/2. So it'll be 1/2, leave the inside alone. And now I'm going to subtract 1 from that power. So this will be negative 1/2 times the derivative of the inside here, which is 4x. And so all of this, what we just found, is just g prime. So I need to finish the product rule by now multiplying by f, which was 6x. And so what this line represents for y double prime here is this is the second derivative without simplifying it. So I'm going to take it that one step further, just showing you how things could kind of simplify and work itself down a little bit. All right, now there's nothing to simplify here in this little first term. This term is just going to carry down. It's the second term that I can kind of simplify, and it's really, again, everything on the outside of what's in parentheses. Excuse me. So this 1/2 here, this 4x here, and the 6x here. I want to go through and combine these three things. I'm multiplying all of them together. So 1/2 times 4x is 2x, times 6x is 12x squared. And then again, my parentheses will stay here to the negative 1/2. And we're going to leave this here. The book will take it a little bit further. We're not going to go any further with this, at least as part of this video right now. If you would like to see this worked out and simplified further, so like if this asked you to find triple prime, we wouldn't really want to leave this as is. We would want to simplify this one more time, just so our derivative wouldn't be as complex and complicated. But for now, we'll leave this here. And it'll be the same, even if this was an assessment or in your homework, you could leave this here. So let me know outside of this video during office hours or some other time during the day as you're working on this. Shoot me an email or respond in the GroupMe, and I'll jump right on and we can kind of work through this together through the whiteboard feature on Zoom. So just let me know. All right, so the last thing I want to look at is an applied example, and I think this is the last thing that I really even want to do. Yeah, so this is the last thing I want to do here. And so I want to look at an example because if you think again what derivative is referring to when you find the derivative of an item, when I do f and I find f prime, what f prime is telling me is it's describing how f changes. And so every time you find the next derivative, it's talking about and describing the previous function. So if I'm going to go through and derive f prime to get f double prime, then what this is actually talking about and describing is describing how f prime itself changes. If we find the third derivative describes how the second derivative changes. And this would work down and down and down, almost like a ladder. And so take a look at this applied example. It's a physics style example. And so this, all the wording and stuff like that should hopefully be a little familiar. But it says this, acceleration of a maglev. So this is a magnetic train. So something that sits and kind of floats and levitates. It's pretty cool, like a high-speed train. Refer to the example on pages 101, 102. The distance covered by a maglev moving along a straight track t seconds after starting from rest is given by the function s is equal to 4t squared. And this is from 0 to 10. What is the maglev's acceleration at any time t? All right, now what this is, when it says like refer back to the pages, this problem was talked about earlier in the textbook and we just didn't really look at it that much. And so I'll go ahead and talk about it essentially now. This function here, the beginning piece, is all about the position. Think about it in terms of distance. Something is traveling. So if I find s prime, so if that's what s is, if I find the derivative of that, then what I'm finding is a function that describes the change in position relative to change in time. In other words, change in distance over change in time. This is velocity, right? Displacement over time. And so what that tells me then is that the derivative of position is a velocity function. So if we derive this position function here, which is pretty straightforward, s prime is 8t. And now what this function will tell me is the velocity at any time I care for. So if I'm looking at if t is running from 0 to 10 seconds, if t is 4 seconds, then I know my velocity, oops, sorry about that. I know my velocity at 4 would be 32. And this would be feet per second, since this is measured in feet per second. Well, what if I take this in another higher order? What if I derive this again? So if I find the second derivative of my position, this would be the first derivative of velocity, meaning that what this would describe would be a change in velocity relative to a change in time. And this, by definition, is acceleration. So what the derivative of velocity gives me is the acceleration at any time t that I care for in terms of my position. And so in this kind of problem, if this is my velocity right here, if I derive this, I would get 8. And what this represents is the acceleration at any time, which notice it's constant. So the acceleration never changes. The acceleration in this problem would be 8 feet per second squared. And that would actually answer this question and why the phrasing of it is at any time t, and why they didn't tell you to find the acceleration at a specific moment. And so just in short, and just to kind of put all this together, especially for a physics style problem like this, again, when you start with position, its derivative gives you velocity. The derivative of velocity gives you acceleration. Acceleration describes how velocity changes. Velocity describes how the position is changing in terms of how it's looking back. And so you'll see a couple problems. They're not even, you may see like 1 or 2 physics problems in the practice, but most of the problems are really just about interpreting what each derivative represents. And so just using like this language here is probably the biggest thing that I want you to take away. is that as you go higher in your derivatives, they're always looking prior. And there is a connection between the second derivative and the original first function, and we'll dig into that a little bit more. And which would make sense again if you think about the physics, that acceleration does play a role in how your position is changing. If you're accelerating, your position is probably going to be changing more or less, not necessarily slowing down or speeding up, but just in terms of its connection with velocity and then in turn its connection with position. So take a look at the practice problems. It's a pretty short day again today. Let me know in the group me if you have any questions, and I'll try to have a class-like meeting at a time that works for y'all, just to kind of check in and see how everybody's doing, and see if y'all all want to meet up in one Zoom meeting. So just let me know, email me, and look forward to when I can see y'all.